Let's use a simple example to discuss Bayes' rule. So let's suppose that during a routine physical exam, a middle-aged man, Joe, tests positive for a disease. There were no previously known indications that he had this disease, but he's panicking. He knows now that he must have it, but can we say that for sure? Let's suppose that only 1% of all undiagnosed middle-aged men have this disease. Also suppose the test that Joe took is not totally accurate. So for middle-aged men who don't have the disease, there's a 10% chance that they will test positive, or the false positive rate is 10%. For middle-aged men who do have the disease, there's a 5% chance that they will test negative, which is the false negative rate. So with a positive test result, what is the probability that Joe actually has the disease? And this is where we're going to use Bayes' rule. And first we're going to break it down, and then we'll go and practice the calculations. So for our 10,000 middle-aged men, out of them, 1% will be undiagnosed and have this disease. So 100 of those 10,000, and 99% will not. Of the 100 with the disease, 95 will test positive and 5 will test negative. Of the 9,900 without the disease, 10% will test positive and 90% will test negative. So we want to know whether or not Joe is one of these 100% or 100 men with the disease who tested positive, or if he's one of these 9,900 without the disease, of whom 10% tested positive. So his chance of having the disease given a positive test using Bayes' rule is going to be 95 divided by 95 plus 990. So here's our 95. And then our 95 plus 990, or 8.75%. His chance of having the disease given a negative test would be 5 divided by 5 plus 8,910, or 0.06%. So his overall chance of testing positive is 95 plus 990 out of the 10,000, or 10.85%. Since the question we were asking was whether or not he has the disease given a positive test, we're looking at this probability here, this 8.75%. So even though he tested positive, there's actually still a very low probability that Joe has the disease, less than 10%. And so panicking is not warranted, well, depending on the disease, I suppose, at this time, until obviously they can gather further information. But does this surprise you that a test with a low false positive rate could result in such a low posterior probability? And if it did surprise you, you're not alone. Highly trained physicians posed with the same problem and asked to guess the range could not converge on anywhere close to 8.75%. The responses in the study were all over the map, anywhere between 0 and 100. So we tend to believe that Joe doesn't have the disease until we see convincing evidence to the contrary. And that's one of the reasons why we should not be surprised that he has such a low probability of having it, because of 10,000 middle-aged men, remember, only 1% of them are going to have the disease. So we need to keep that in mind. And then also this test, the error rates with 10% false positives and 5% false negatives is going to also skew his results down even more. So a more accurate test with a better false positive rate would change this number quite a bit. Okay, so let's work through these probabilities ourselves, and then in your assignment, you will be asked to add an additional possible response to the test and recalculate the posterior probabilities. So we know that the prior probability was 1% of having the disease and 99% don't have it. And that relates to this first node on our decision tree over here. Then we need to know, in order to calculate Bayes' theorem, which is the likelihood times the prior divided by the sum of the likelihoods times the priors. So we need the probabilities that indicate the actual accuracy of the test. So this will be, we know that if you get a positive test, there's a 95% chance that you have the disease and a 5% chance that you don't. And then if you do not have the disease, there's a 10% chance that you get a positive test and a 90% chance that you get a negative test. So the first thing we need to do is calculate the sum of the likelihoods times the priors, or the Bayes rule calculations, so the probabilities of the test results. So in order to calculate those, we're going to use the sum product formula of the diseases, which I'm going to go ahead and fix, and these positive probabilities here. And then we're going to calculate the same sum product for the negatives. And now we have the sum of the likelihoods times the priors. So now we can go ahead and do our next calculation. For this calculation, we're going to take we'll start with the positive and the having the disease. So the likelihood of that times the prior likelihood divided by the sum of the likelihoods times the priors, which we calculated first. I'm going to go ahead and make my life easier by fixing that value there. Okay, and then I can copy the formula over and down. I had to fix my formula. I fixed the wrong thing, so I want to hold the row 4 here, and then I want to hold column B here. So fix that real quick, and then I'm going to go ahead and drag my formulas down and over. Okay, so the likelihood times the prior divided by the sum of the likelihoods times the priors. Same here, negative times the prior of having the disease, and then the sum of the likelihoods times the priors. Double checking all my formulas. No disease, no disease, probabilities of the test results, and no disease, and a negative, no disease, and then the negative over here. And if I look at my sums, I have sums of 1 going down, which is great. That's what we want to see. So now we've calculated the posterior probabilities given test results. So given a positive test result, the probability of actually having the disease is 8.8%, and the probability of not having it is 91.2%. And then given a negative test result, the probability of having the disease is very low, 0.1%, and then there's a 99.9% chance of not having the disease given a negative test result. Okay, so for the assignment. For your assignment, we're going to add another possible scenario to our test results. So instead of just positive and negative, we're also going to have a maybe. So given this new possible test result, maybe we're going to take the 2x2 range in cells B9 to C10, and we're going to replace them with a 2x3 range. And this is going to break all of these formulas, so let's go ahead and clear these out really quick. Okay, and then our new possible result is going to be maybe. And the corresponding probabilities are now going to be 0.85 for positive, 0.10 for maybe, 0.05 for negative. So those sum to 1. And then for the new probabilities in row 10, we have 0.05, 0.15, and 0.8. Once again, they sum to 1. So for your homework, you're going to take this file and you're going to calculate the same calculations we did to get the posterior probabilities, except now you have the additional test results here. So process is the same. First, calculate the probabilities of the test results, use your sum products, and then use Bayes' formula here to calculate your matrix of posterior probabilities.